All right, so here's a function f and some kind of a secant line. You guys know what a secant line is?
Yeah.
Yeah.
So a secant line is going to be a line that passes through a function twice.
Oh.
A secant line is a line that passes through a function twice at a kind of local scale.
What if it's 3 times?
Then it's double
It's a
secant.
triple secant. Okay, so it's more than 1.
Yeah,
Because one would be.
except that
One is the longest.
It cuts a graph.
there's some confusion with this because tangent lines can pass through twice as well. It's on a local scale. So locally this thing passes through twice. Tangent lines locally pass through only once. So this line passes through this thing twice. And I want to talk about the average rate of change here. So what I mean is how fast is f going up if I move over? You guys see that? So my best guess for that is some kind of like, okay, here's an orange thing, right? I ballparked again like we did earlier. And now let's say, what's the average here? So what's the slope of the orange thing? Awesome. So this thing has a slope, right? That's a rise over a run. And that's a change in f divided by a change in how about a change in x? Which in this example, right, is from x to x plus h. So how much is the run there? H, I think. And what's the change in f? Ooh. How about this? Do you guys know the y coordinates for these 2 points?
Oh.
So they're points on the what? They're points on the graph. So they're x comma f of x pair, right? And this one is a x plus h, oops, comma what? F of x. Awesome, right? So what's the difference between the y values? Careful. There's grouping symbols in the way. So I think it's f of x plus h minus f of x. You see that? So our slope of a secant line is f of x plus h minus f of x all over h. That should go in your head. Or your nose. Okay. Should we do this another way? Because this gets represented 2 different ways in your book and lots of books. So I'm going to run through this exact same thing. Don't panic. I'm just going to change a couple of numbers. Well, letters. So I'm going to dump the x's. Oops, that's still going to be f. Okay, so I just dumped a couple of things, really the x and the x plus h. So I'm going to run this exact same thing with an a and a b. Okay, so let's make sure we understood. So what are the coordinates of this first point over here? This is still a function f of x. So this is a and f of a. Good? And this one is b and f of b. Okay, see that? They're an input-output pair. The input's an x thing, and the output is just f of that x thing.
Okay, so can you show B like on the graph? Because I'm not understanding where B is. Is B on the x-axis? Or
Yeah. What if I did that?
Okay. Yeah, that makes
I just have been avoiding attaching axes to this because I don't want to deal with the coordinate system.
Yeah, no, that's fine. I
Right,
just
so
didn't
this is
know
not
where it was.
necessarily 0, 0, it's just somewhere.
I understand that.
Cool. All right, so what's your change in f over change in x? Can you read that? What's your change in f now? F of b minus f of a over b minus a. Cool. So this is an alternate form of the slope of a secant line. That's f of b minus f of a over b minus a. Now, what are the units on these? These are what's called average rates of change, or slopes of secant lines. But what are the units?
Depends.
Yeah, it depends on what the units in the problem were, right? So assume that y had some units and x had some units. What are the units on these things, then? These are going to be in close. I did rises over runs, right? So these are going to be in y units over x units. And these are y units over x units. You guys cool with that? You want an example? Okay. So, for example, say the x-axis was time and the y-axis was position. Right. So, suppose I had this little picture. I had time this way and position this way. Say I'm measuring this one in meters and this one's in seconds. Right? So there's some kind of thing going on here. What are the units of one of these secant lines in? These are in meters per second, which means that they're yeah, they're a velocity. You guys see that?
And then if you find a slope that's either accelerated, or is that usually?
So if I make one of these secant lines, right, and I find that, oops, I make one of these secant lines, and I find the average slope there, that's going to be the average velocity. You guys see that? So this slope is average velocity. If I run the same thing with, instead of a position, if I run it with a velocity function, then my slopes of my secant lines are average accelerations. You guys pull that?
Say that one more time, that last bit.
So if we start with this ladder, say we had a position as a function of time, right? Okay, so this thing has units like meters or something. If I calculate a rate of change, right, I'm going to end up with something like meters per second as my unit. That's a velocity. So the rate of change of position is velocity. And the rate of change of velocity is acceleration. And what are the units on acceleration?
Meters per second per second.
Yeah, they're going to be meters per second per second. Right? They're going to be the units of the thing above divided by time. What's the next one down? You guys know? Anybody engineer enough to know this? So what's the rate of change of acceleration? Okay, so where do you find these? In your car, the position is what? There's a dial that has this on it. It's not your speedometer. Speedometer is this one. Yeah, the odometer is this one. Right, that's literally just how far your car has ever gone. The rate at which your car is going is the speedometer.
That's how fast it's moving.
Yeah, this is a function of your tach. If you stayed in one gear forever, this would be your tach. Otherwise, this is your, oh no, sorry, I lied. This is the gas pedal. It's not your tach. Cool? What's the next thing down?
How fast your gas pedal is moving.
Yeah, how fast you're popping on the gas, right?
Okay.
Or how hard you're slamming the brakes, alternatively.
Yeah.
When you slam the brakes really hard, what does the car do?
Accelerates.
Yeah, it's accelerating, right,
Yeah.
backwards really fast. It's jerking, right? This last thing is called the jerk function. Cool. And what are the units on that one going to be?
Jerky.
Jerky. They're going to be meters per
Jerky.
second per second per second cube. Yeah, so they're meters per second cube. Cool. You guys believe that this could be a useful theory?
Yes. It is.
This is where rocket science starts.
Well, it's also
Cool.
how like you engineer to like how much gas per like where you're putting on it.
Mhm.
Throttle it to.
Yeah.
Because you don't want to have all the gas at like 1 inch of pedal.
Yeah. Yeah, you want to make sure those functions are reasonable.
Yeah.
All right, any questions on how to do rates of change? Okay.